Picture this. It's mid-March 2026.
Oh, wow. Yeah. Oh, yeah.
You are looking out over the Strait of Hormuz, which is, arguably the single most critical maritime choke point on the entire planet.
Absolutely. The bottleneck for global energy.
Right. Normally, you'd look out and see this constant churning flow of massive merchant ships carrying, the bulk of the world's energy supplies. But instead, exactly, you see these paralyzed giants. Ships are just sitting there, anchored in dead silence. Transit through this specific corridor has completely shifted from a totally routine passage to, a high-risk, invisible electronic warfare zone.
Yeah, the visual of those massive steel mountains just sitting at anchor, like literally afraid to move, it really captures the gravity of the whole situation.
It's terrifying.
It is. And these aren't ships that have suffered, a catastrophic mechanical failure. They haven't lost their engines. They basically lost their reality.
Yeah.
The digital environment they rely on to navigate has become entirely untrustworthy.
Which brings us to the core mission of today's deep dive. We are unpacking a gripping maritime analysis from a publication called The Deep Draft. It's written by Captain Raghu Sharma.
A fantastic piece. Really eye-opening.
Truly. And to give us the hard technical framework, we are layering that with an official, highly detailed technical report from Intertanko.
Right, getting both the operational and the engineering perspective.
Exactly. We are going to figure out how invisible electronic signals are literally hijacking the navigation of multi-million-dollar vessels, forcing the global supply chain into a complete standstill.
The scale of the disruption detailed in these sources is it's staggering. We're looking at a fundamental threat to global trade, and it all hinges on vulnerabilities in navigational systems that, honestly, the entire modern world just takes for granted.
Yeah, to give you a visceral sense of just how tense things are in the Gulf right now, look at the events of March 14th, 2026.
Right, the LPG carriers.
Yes, 2 Indian-flagged LPG carriers, the Shivalik and the Nanda Devi. They became the first vessels in nearly 2 weeks to actually cross the strait.
2 weeks of nothing, then them.
And they were carrying a highly volatile liquefied gas, so they couldn't risk the transit alone. They required a close escort by an Indian Navy warship under a military initiative called Operation Sankalp.
Which is wild for commercial shipping.
It's unprecedented. And the maritime intelligence statistics coming out of this region, they explain exactly why they needed that warship. Authorities recorded over 1,700 GNSS, that's Global Navigation Satellite System Interference events, in just the first few weeks of 2026 alone.
Yeah, and the maritime analytics documented a single 24-hour window where over 1,100 vessels were simultaneously spoofed.
1,100?
1,100.
In one day.
A coordinated invisible attack essentially kidnapped the digital presence of over 1,000 ships, manipulating their systems to make it look like they were sailing toward inland infrastructure or, airports and military bases.
Okay, let's unpack this.
Yeah. So as we dive into the mechanics, consider how you interact with GPS on a daily basis. For you, losing a satellite signal probably means taking a wrong turn on the way to a new restaurant, or maybe your fitness watch missing a mile of your run.
Exactly, an annoyance.
But for the master of a 300-meter-long tanker operating in restricted waters, that little blue dot on their electronic chart is not a convenience.
No, not at all.
The mathematical integrity of that single blue dot is the literal boundary between safe commercial passage and a catastrophic international incident.
So to understand how a single corrupted, invisible radio signal can bring a massive physical ship to a halt, we have to look under the hood of the modern ship's brain.
Right, the central nervous system.
The maritime industry calls this the Integrated Bridge System, or IBS.
Yeah.
We've moved far beyond the days of a bridge having distinct isolated stations for different tasks.
Oh, entirely.
Yeah.
Over the last 2 decades, satellite navigation went from being just, one standalone sensor sitting in the corner of the bridge to becoming the foundational heartbeat for almost every piece of technology on board.
It feeds everything.
Everything. The GNSS feed drives the ECDIS, the Electronic Chart Display and Information System. It automatically aligns the radar overlays so the radar blips actually match the map. It feeds the AIS, which broadcasts the ship's identity and vector to surrounding traffic.
See, I have to push back on the architecture of this setup.
Oh.
Yeah, it seems completely counterintuitive for the maritime industry, which is famously obsessed with redundancy, to design a ship where highly advanced safety systems all share a single point of failure.
I hear you. It defies conventional risk management.
Right.
But that is the reality of the modern integrated bridge.
It's crazy.
The dependency goes far beyond mapping. Critical communication arrays like the GMDSS, the Global Maritime Distress and Safety System, rely on that satellite feed.
Wow.
Even the ship's Voyage Data Recorder, which is basically the maritime equivalent of an airplane's black box, pulls its ultra-precise timestamping and georeferencing directly from that exact same GNSS signal.
So it's all tied to the clock.
Exactly. The global satellite network provides atomic clock-level timing precision, and modern bridge computers just devour that data to keep their internal networks synchronized.
So to put this in terms of like driving a car for you listening at home, imagine you're cruising down the highway at night, relying on your dashboard GPS. Suddenly, a satellite glitch doesn't just freeze your map.
Right.
That single data error causes your speedometer to plummet to zero, your headlights to shut off, your collision warning sensors to start shrieking, and your engine diagnostics to completely crash all at the exact same millisecond.
That analogy perfectly captures the cascading failure. Captain Sharma in the Deep Draft specifically refers to this as the digital cascade.
The digital cascade, yeah.
When the GNSS receiver swallows a compromised signal, the bridge doesn't just quietly lose its digital map. The ship experiences a violent, widespread, simultaneous equipment panic.
Because the AIS, the distress radios, the radar processors, and the black box are all suddenly being fed contradictory or invalid data simultaneously.
Yeah. And the psychological impact on the bridge team is severe. It triggers overwhelming alarm fatigue.
I can only imagine.
Picture a bridge crew navigating through heavily trafficked waters in the dark. In an instant, every single console around them starts blaring distinct, high-decibel warning alarms.
Just chaos.
Total chaos. The ECDIS flashes an invalid position error. The VHF radios chirp with a position feed loss. The echo sounder alarms trigger.
So what do they do?
Well, the immediate human instinct is to stare down at the screens, frantically mashing buttons to silence the alarms and troubleshoot the software.
Which means the crew is essentially trapped in a localized IT crisis.
Exactly.
They're spending critical minutes trying to figure out which computer broke rather than simply, I don't know, walking out to the bridge wing, looking at the actual water and confirming where the physical steel ship actually is.
Right. The bad signal completely shatters their situational awareness by distracting them with digital noise.
Yeah. Now, the Intertanko report transitions nicely from the vulnerabilities of the bridge to the actual mechanics of how these attacks are executed.
The tactics.
Right. They divide the electronic warfare threat into two distinct tactical categories, jamming and spoofing.
And to distill it to its essence, jamming is designed to make the receiver die, whereas spoofing is designed to make the receiver lie.
That's a great way to put it. Let's explore the mechanics of die versus lie, starting with jamming. The physics behind jamming are actually surprisingly straightforward.
Oh yeah, it's very basic.
It is literally a brute force denial of service attack. The attacker broadcasts raw, high-power radio noise on the exact frequency bands used by GNSS satellites.
Which works because those satellites are orbiting in medium Earth orbit, roughly 12,000 miles above the planet. So their signals are incredibly weak by the time they reach a ship's antenna.
It's like trying to listen to someone whispering a secret from across a crowded room while someone standing right next to you starts blowing an air horn.
That's spot on. The inverse square law of radio frequency propagation basically guarantees the local transmitter always wins.
Right.
The ship's receiver simply cannot distinguish the satellite's whisper through the localized screaming of the jammer, so it loses its cryptographic lock on the satellites.
But Intertanko points out something: while jamming is not strictly the domain of military actors.
Oh, no, it can be entirely accidental.
Yeah.
A ship's own Inmarsat communications dome, broadcasting at just 25 watts, can completely drown out or even physically fry a nearby GNSS receiver if the shipyard didn't properly isolate the antennas during construction.
That is insane. But I guess the silver lining with a jamming attack is that the ship immediately knows it is deaf.
Yes.
The screens instantly flash loss of position. Alarms notify the crew that they are navigating blind, which forces an immediate transition to traditional manual navigation methods.
Right. They know there's a problem. Spoofing, on the other hand, is infinitely more deceptive.
Because it's lying.
Exactly. Instead of blasting noise to block the receiver, a spoofing transmitter broadcasts meticulously forged satellite data. It feeds the ship what the industry terms hazardously misleading information.
And the ship's computers process this fake data, fully believing it to be a pristine, high-integrity signal from space.
Yep. The digital map updates smoothly, the alarms stay completely silent, and the crew believes everything is proceeding normally.
The Intertanker report highlights a fascinatingly lazy but devastatingly effective version of this called meakening.
Oh, meakening is wild.
The attacker doesn't even bother writing a complex algorithmic fake signal. They just set up a receiver, record a completely genuine GPS broadcast from one location, and then blast it out over a different area like a delayed tape recorder.
Which perfectly explains those bizarre accidental meakening incidents you see around coastal airports.
Oh, right. The hangar thing.
Yeah. A maintenance crew inside a thick concrete hangar will set up a GPS repeater to test aircraft avionics indoors. If they accidentally crank the gain on that repeater too high, the signal leaks out over the water.
And chaos ensues.
Right. Suddenly, every merchant vessel sailing past the nearby harbor receives a pristine, mathematically perfect satellite signal, insisting they are currently parked on runway 27L doing 150 knots.
Okay, here's where it gets really interesting. Because while jumping from the ocean to an airport runway is obvious to any crew paying attention, the deep draft details a highly sophisticated, insidious tactic called the carry-off attack.
This is the scary stuff.
It really is. This isn't a sudden, jarring teleportation across the map. It is a calculated, creeping abduction of the ship's navigation system.
The choreography of a carry-off attack is terrifyingly elegant.
Seriously.
The hostile transmitter first aligns itself perfectly with the vessel's authentic GNSS signal. It broadcasts a fake location that mirrors the ship's actual location down to the millimeter.
So the ship's receiver has absolutely no idea it is now listening to a hostile transmitter on a nearby shoreline instead of a satellite in orbit.
Exactly. Once the receiver is locked onto the hostile signal, the attacker begins to slowly, incrementally alter the pseudo-range data in the broadcast.
Or just tweak it.
Yeah. They don't jerk the vessel 3 miles to port. They gently, mathematically drift the calculated position.
And this gradual drift is specifically designed to defeat the mathematical safeguards built into modern receivers, a system called RAIM.
Receiver Autonomous Integrity Monitoring.
Right. RAIM is constantly doing geometry. It looks at the distance calculations from 5 or more different satellites. If one satellite says the ship is somewhere else, the lines don't intersect, and RAIM instantly flags the signal as corrupt.
But in a carry-off attack, the attacker subtly shifts all the mathematical ranges simultaneously. The math still creates a perfect intersection, just in the wrong physical location, so RAIM never triggers an alarm.
Wow. Furthermore, the human crew is just as likely to be fooled.
Oh, absolutely.
If you are the officer of the watch, and you notice your digital ship slowly drifting slightly left of the planned track line, your instinct isn't to assume an invariable cyber attack.
No, you assume you're experiencing natural tidal drift or a shifting surface current.
Exactly. You casually adjust the autopilot a few degrees to compensate.
Yep. In reality, the ECDIS is showing a perfectly safe track, while the autopilot is physically steering the 150,000-ton steel vessel silently off course, potentially straight into a shallow reef or hostile territorial waters.
Captain Sharma makes profound observation here. Jamming tells the bridge it is blind, which breeds immediate caution. Spoofing convinces the bridge it can still see perfectly well, which creates a false and potentially deadly sense of security.
100%.
Which brings up a critical question. If the digital map is lying and the ship's internal computer math is being successfully manipulated, how does the bridge actually catch the deception?
Well, the defense mechanism relies on how the ECDIS handles the loss of absolute positioning. The systems are engineered for what developers call graceful degradation.
Graceful degradation, I like that term.
Yeah, when a GNSS receiver eventually detects a signal loss, the ECDIS doesn't just crash to a blue screen. It automatically transitions into dead reckoning or estimated position mode.
It essentially takes the very last known verified satellite fix and then starts predicting the ship's movement across the digital map using purely internal sensors.
Right, specifically the ship's gyro compass to know which direction it's pointing and the speed log under the hull to know how fast it's moving.
But the danger emerges because dead reckoning is entirely based on vector mathematics, and those internal sensors are prone to cumulative error.
They absolutely are. Gyro compasses experience mechanical friction and drift due to the Earth's rotation. Speed logs suffer from calibration errors or biofouling on the hull.
Algae and stuff.
Exactly. You add in external variables like wind pushing the superstructure and ocean currents pushing the keel, and the predicted digital position slowly begins to peel away from the actual physical location of the ship.
So to combat this, Crews have to become detectives, looking for specific telltale signs of a hijacked reality.
Right.
The Deep Draft documented incredible anecdotes from the Black Sea and the Gulf where crews spotted these anomalies. The most glaring red flag is a radar overlay mismatch.
Oh, this is a big one.
Modern bridges project the raw, bouncing radar returns from physical objects directly on top of the digital ECDIS map. During advanced spoofing events, crews would look at their screens and see the solid yellow radar return of a physical coastline displays 2 to 3 nautical miles inland from where the digital map claimed the coastline was.
What's fascinating here is that countering an invisible, highly advanced cryptographic cyber attack suddenly boils down to basic physical cross-checking. You are forcing the digital world to prove itself against the physical world. Another major indicator is a sudden discrepancy between speed over ground and speed through water.
Right, so speed over ground is calculated by the satellite watching your absolute movement across the Earth. Speed through water is calculated by a physical Doppler sensor or a paddle wheel spinning under the hull.
Exactly. So if the GNSS feed suddenly insists you are doing 18 knots over the ground, but your hydrodynamic hull sensor measures only 11 knots through the water, and you know for a fact you are not surfing a massive 7-knot tidal current.
And then you know.
Right, your satellite feed is feeding you a fabricated reality.
You see the same phenomenon with echo sounder mismatches? The digital chart asserts you are sailing in a deep channel with 100 meters of water under the keel, but the acoustic sonar physically bouncing off the seafloor is returning a depth of only 30 meters.
It becomes a high-stakes game of spot the difference.
Really does.
Recognizing that the screen is actively lying to you is the single most critical cognitive leap a bridge team can make.
But acknowledging the threat environment is only the first step. The industry has to actively fight back to keep the global supply chain moving.
Right.
The solution relies on a dual approach, layering technological defenses from the engineers combined with aggressive navigational resilience from the human crew. Looking at the technological solutions outlined by Intertanko, manufacturers are rapidly developing countermeasures.
Starting with multi-constellation receivers. They are the first line of defense.
How so?
Instead of solely relying on the United States GPS network, modern receivers simultaneously pull math from Russia's GLONASS, Europe's Galileo, and China's Beidou constellations.
So you're essentially cross-referencing 4 independent maps of the sky.
Exactly. But while multi-constellation hardware provides excellent redundancy against system failures, it falls short against a dedicated electronic attack, because a sophisticated wideband jammer can simply blast white noise across all those frequency bands at once.
Of course.
That forces the industry to look beyond radio waves entirely, which brings us to aiding the receiver with an IMU, an inertial measurement unit.
This is a purely physical approach, right?
Yeah, purely physics.
An IMU uses microscopic microelectromechanical systems, MEMS accelerometers, and vibratory gyroscopes to measure physical acceleration and rotation. It does not process radio waves, it only measures physics.
Right.
So if the radio signal suddenly calculates that the ship just leaped 3 miles to the port side, but the IMU measured absolutely 0 lateral physical acceleration, the bridge computer immediately knows the radio signal is mathematically impossible and rejects the spoofed data.
It's a great failsafe. And upgrading the antennas themselves provides another layer of hardware defense.
The CRPA, right?
Yep, CRPA-controlled reception pattern antennas. They utilize multiple distinct antenna elements. When a CRPA detects a jamming or spoofing signal, it introduces microscopic delays to the signals hitting its different elements.
How does that help?
This beamforming technology mathematically creates a null or a blind spot aimed precisely in the direction of the hostile transmitter.
Oh, wow.
It effectively turns a deaf ear to the attacker on the coastline while continuing to listen clearly to the genuine satellites directly overhead.
That's brilliant. And the ultimate technological countermeasure, which Intertanko highlights as the future of maritime security, is NMA navigation message authentication.
Which is a huge leap.
This shifts the defense from hardware to cryptography. NMA utilizes asymmetric encryption. The genuine satellite in space holds a private digital key, which it uses to continuously sign the navigation data it broadcasts.
Right. And the ship's receiver holds the public key to verify that signature.
It acts as an unbreakable cryptographic handshake.
Exactly. To successfully spoof an NMA-protected receiver, an attacker on a beach with a laptop wouldn't just need to fake the radio frequency. They would need to steal the private cryptographic key physically secured inside a satellite orbiting 12,000 miles above the Earth.
Good luck with that.
Exactly. The European Galileo system is currently leading the charge in deploying this capability.
But even with quantum-level cryptography and null steering antennas, Captain Sharma's analysis in the deep draft forcefully argues that true resilience does not lie in the soliton.
No, it lies in the people.
He introduces the concept of navigational resilience, arguing that modern seamanship is fundamentally about sensor management. The modern mariner cannot just be a passive monitor of digital systems. They must be a relentless skeptic of their own instruments.
When a vessel enters a high-risk area like the Strait of Hormuz, the bridge team must proactively degrade their reliance on automation.
Go old school.
Exactly. The moment the satellite lock exhibits any latency or suspicious behavior, the crew has to instantly revert to traditional analog methods. They take manual radar bearings, use parallel indexing to physically measure distances off sweeping coastlines, and utilize visual transits.
A specific technique that stood out in the analysis is echo reference mode.
Oh, that's a clever one.
When the GNSS environment becomes a contaminated war zone, the crew can command the ECDIS to drop the satellite feed entirely. Instead, they digitally anchor the electronic chart to a highly visible stationary radar target in the physical world.
Like an offshore oil rig or a prominent lighthouse or a rocky headland.
By locking the map to a physical object 3 miles away rather than an invisible satellite 12,000 miles away, they completely sidestep the electronic warfare domain.
It's so smart. The spoofing signals wash over the ship harmlessly because the navigation is anchored in the physical reality the radar can actually see.
Yeah.
A bridge team that only knows how to blindly follow the blue dot on a screen becomes an immediate victim the second that dot is compromised. But a team that inherently trusts raw radar returns, depth contours, and manual fixes retains absolute command of their vessel regardless of the electronic noise around them.
We have charted a massive course today. We started by looking out at paralyzed ghost ships anchored in the Strait of Hormuz. We stripped down the architecture of the integrated bridge system to see how one compromised timestamp triggers a catastrophic digital cascade of alarm fatigue.
We really covered a lot.
We broke down the brute force physics of jamming versus the terrifying mathematical elegance of a carry-off spoofing attack that defeats integrity algorithms. And we finished by exploring how the maritime industry is fighting back by combining cutting-edge cryptographic antennas with the ancient, unyielding discipline of traditional seamanship. So what does this all mean?
The overarching lesson is that technology, regardless of how interconnected, automated, or brilliant its engineering is, must never fully replace critical thinking and independent verification. The ultimate failsafe on a 150,000-ton, multi-million-dollar commercial vessel is not a secondary backup computer. It is human situational awareness. It is the disciplined cognitive leap required to look at a highly advanced digital display, look out the physical window at the ocean, and realize they do not match.
Which leaves you with a deeply unsettling reality to consider long after this depth dive ends. We have just explored how highly trained professional mariners on massive ships are actively battling to prevent their vessels from being silently hijacked by spoofed signals from space.
Yep.
Now, look at the infrastructure of your own daily life. Consider the fully automated systems we're increasingly handing control over: self-driving cars, navigating high-speed interstates, automated delivery drones operating in urban airspace, or even the microscopic timestamps that govern billions of dollars in algorithmic high-frequency trading on global financial markets.
It's everywhere.
How vulnerable is the architecture of our modern world, given that almost all of these automated systems blindly, completely, and unquestioningly trust those exact same invisible, unverified signals falling from the sky?